we are going to understand a few things here. First of all, change in concentration, change in temperature, change in surface area. Okay. All of these things, how do they affect, and addition of a catalyst. So how do these things affect the rate of reaction? We are going to look at each one of them, but through the eyes of a experimental process. Okay. So there are certain things which speed up the chemical reactions, others will slow down the chemical reaction. We should know exactly what is what. Okay.
Yeah.
Now, before I start with that, I want to look at certain thing known as variables here. You can see on the right hand side, there is a topic known as the variables in this case. What are variables? These are factors you can change in a experiment. So these factors can be changed during the chemical reaction. Okay, so that hence these are referred to as variables. To find the effect of variable X on variable Y, you keep all the other factors unchanged or controlled. Okay, do you understand my point? Okay, so if
Yeah.
let's say you want to understand that what is the effect of X on Y in this case, then you need to keep every single thing constant, okay, or unchanged in this case. This is known as a controlled system, okay. This lets you focus on how X affects Y, okay. So the variable you choose to change is known as the independent variable, whereas Y is known as the dependent variable. Why? Because by changing X, you are looking at how Y is affected here. Do you understand my point?
Yeah.
Okay, so coming to the experiment here, if I change concentration, pressure, temperature, volume, okay, these are independent variables. Okay, do I get your
Yeah.
attention here regarding these? These are independent variables. Temperature, concentration, volume, pressure, even catalyst. These are independent variables.
Independent.
Whereas what is dependent on it? The rate of reaction. Okay, rate of reaction is the dependent variable here. Okay, which you can see clearly in the experiment, the independent variable is concentration. The dependent variable is volume of the gas produced, which is obvious. And volume of gas is directly proportional to the rate of reaction. Okay, so volume of gas produced will be the dependent variable for this particular case. Understood? Okay, let's come to the experiment
Yeah.
here. So first part we are going to look at that how changing concentration is going to affect the rate of reaction. Okay, so here is the situation. I have taken the same setup as I did in the last class. If you remember, there is a round bottom flask. Okay. There is hydrochloric acid, and in hydrochloric acid, I have added a zinc um, piling, okay, or turning in this case. Now, what I've done is I've taken a stopcock. There is a what is known as a delivery tube, and then there is a syringe with the plunge completely at the zero level, right? You can see that it is the same case. But look at the concentrations of hydrochloric acid. In the first case, you have taken 50 centimeter cube of some, you know, concentration of hydrochloric acid. Look at the second one. The concentration is twice in this case. So what do you expect? You would expect that the reaction in the second case will be faster. Okay. But how about the rate of reaction? How fast would be the rate of reaction? This is the result. Can you see? In case of A,
Yeah.
the reaction occurs at a less steeper rate, right? It is more lenient in this case, and the graph is situated at 45 degrees, where you can see that the reaction gets over somewhere around here, right? Somewhere around 114 and 116, right? In terms of
Yeah.
seconds. But the thing, so in both the cases, the reaction occurs at a similar time. But look at how B occurs. Okay, how B occurs in this case. B occurs at a much faster rate. The slope of the reaction is much, much steeper in this case. See how it is. Okay. It is much steeper in this case. Okay. If I were to consider the bond angle from the bottom, you can see that the angle in this case is quite large. Right? Do you agree with my finding? So you can see that the rate of reaction initially in the middle, okay, is much faster. And if you consider the overall average rate of reaction, it would be faster as well. Okay. So where was I? I was talking about this part where I was talking about the result. Okay. So coming to the A part had about 50 centimeter cubes of some concentration of HCl. You have magnesium filing in that case. Okay. zero point 0.5 grams about of it. In the second case, 0.05 grams of magnesium are still there. But now what you are doing here is 50 centimeter cube of HCl, but the concentration of HCl is twice as strong. Okay, so you can see that the graph gives you an apt observation of how it actually works. Okay, so what I want you to do is I want you to take the results and take the conclusion of the results. Okay, which is written below. So I want you to take note of those and then we'll discuss. Okay. We're discussing about the results of a chemical reaction where how is the rate of a reaction affected when we change the concentration. Okay. Anyways, I'm saying that so for the first case, the concentration is half the case when you consider the second scenario where the concentration is doubled in this case. Okay, concentration of what? Concentration of hydrochloric acid. Okay, how is that affected? Let's look at the wordings here. Okay, so point number one, curve A is much steeper than curve B is much steeper than curve A. So the reaction was faster in B. Okay. Curve B is steeper than curve A and the reaction was faster, which is obvious. It should be. Right. If you look at how much time it took for the reactions to occur, look at B. B occurred somewhere around 60-58 seconds, right? So in B, the reaction lasts about 60 seconds, and in A, it lasts at least for 120 seconds. I would say somewhere around 115 or so, but you get the idea. Okay, both the reactions produce 60 centimeter cube of hydrogen. Do you agree? The answer is yes, because if you were to extrapolate this line on the y-axis, okay, you'll see that in both the cases, the lines conclude or the lines intersect at 60 centimeter cube here. Do you guys agree what I'm trying to say? Okay, so the amount of substance which is produced, it is the same. Think of it like the case of a run. Okay, if you're doing a marathon or a sprint in this case, the path is the same. Okay, and the people who are running are the same. But the thing is, some people run at a faster pace, some people run at a mediocre, and some at a very slow pace. Okay, so everyone reaches the same tracks. Okay. But the thing is that they reach at different intervals of time. So where was I? Yeah. So in this case, by so where was I? Yeah, I was talking about a marathon or just a race, normal sprint race in this case. So the tracks are the same, and the amount of time that is taken by every single person can be different because of different conditions associated, right? So here also the same thing happens. So if you read the fourth point here, you will see one thing that what is written. So in B, the average rate was 1 centimeter cube of hydrogen per second. Okay, that's the basic idea. But in A, it was about zero point 0.5 centimeter cube of hydrogen per second. You can calculate this very easily. They have also given the idea. So the average rate of reaction in B was twice the average rate of reaction in A. Okay, so what do we come across with this? Okay, reaction goes faster when the concentration of reactant is increased. Okay, this is the basic point we have learned from this. Okay. Now this brings me to the next one. What happens when we change the temperature? Okay. Now rate of reaction is obviously affected by temperature here. So therefore temperature is the independent variable. Okay. And rate of reaction is the dependent variable. Understood? So in this case, again, a similar reaction is there. No, a different one. Dilute hydrochloric acid is there, which was the same in the previous one. But now we are using something known as sodium thiosulfate. Okay. So by adding these two, what we'll get is we'll get a yellow precipitate of sulfur. Okay. So how do you follow this reaction? By the way, why am I doing these reactions with you? Because the thing is, you can get questions, as I said it earlier, you can get questions as case studies, okay? And you will have to answer on the basis of those case studies in this case, as simple as that. Okay, what happens in this case? You take a circular paper in this scenario, mark a cross on the circular paper, okay? Place the beaker containing sodium thiosulfate solution on top of the paper. So basically, you take the paper, okay, you put it in a beaker which would fit that paper. So in this case, we usually do it with a 100 centimeter cube beaker in this case, okay. So we put the paper at the bottom of the beaker, place the beaker containing sodium thiosulfate. So you pour down sodium thiosulfate on top of the paper. Okay, basically what it does is it improves the visibility of the reaction. Okay, it improves the visibility of the chemical reaction. Now, in the same case, what you do is you take the the paper and the solution on top. Okay, the beaker all together, and then you add hydrochloric acid from the top to it. Okay, so you add it very quickly and start the clock at the same time. Okay, so you add it, start the clock. Do you understand? Mix and quickly measure the temperature of the mixture. Okay. So the moment, so you must have a thermometer. Okay. You can put a thermometer inside, add HCl and start the clock. Okay. These three things have to be done very, very quickly. You cannot wait for about 5 seconds or 10 seconds. Within a second or two, you have to quickly adjust every single thing. Okay. So you measure the initial temperature and then you measure the temperature at different intervals while the clock is running. Okay. So you'll see that the cross which is drawn on the paper in the middle tends to fade away, as you can see, right? See, in this case, how it is fading away in this scenario. Okay. Till the point the cross completely disappears. So the cross goes fainter as the precipitate forms. Stop the clock the moment you can no longer see the cross. Note the time. All right. Now, what you need to do is you need to repeat the same set of steps, but you need to measure the changing temperature in this case. Okay. You do this by heating sodium thiosulfate to different temperatures before adding the acid. Okay. So here are the results based on it. Okay. You don't need to write the experiment, just understand how this works. So in this case, you have the temperature of the mixture at 20, 30, 40, 50, and 60 degrees Celsius. Look at the amount of time that has taken in order to complete the reaction. In the first case, it is 200 seconds. In the second case, 120, 50. And if you look at the last one, the amount of time has reduced by 1/10 in this case. Okay, almost 1/10. So from 200, you now have 24 seconds. So what does this tell you? That the cross disappears when enough sulfur has formed to hide it. Okay, so the reaction is about how much? If you look at 40 seconds and 20 seconds, about 4 times as faster. So a reaction goes faster when the temperature is raised. The rate generally doubles for an increase of 10 degrees in this scenario. Okay.